measure then? I'm going to talk about measuring angles in radians rather than degrees, and then how that applies to movement in a circle, which we sort of talked about briefly before the break when we were talking about those angles greater than 90 degrees, and define angular velocity. So first of all, a definition of radian. The radian is a measure of angle, and it's defined as the angle subtended at the center of a circle. So in other words, the angle is measured from the center of a circle going round by an arc equal in length to the radius. So if this arc length S equals the radius, then we've got 1 radian. So theta would be 1 radian. And if we do that, then that means that the arc length S equals the radius times the angle measured in radians. So that's the first formula to do with radian measure, is that the arc length S equals the radius times the angle measured in radians. So if you think about this definition, if we've gone round a distance equal to the radius, we've gone round 1 radian in other words, then 2 pi times the radius is the complete turn. So if we're measuring our angle in radians, then a complete turn is 2 pi radians. So 1 complete turn is 2 pi radians. Therefore, 2 pi radians is equivalent to 360 degrees. And that's what we use to convert from one to another. So if you remember that 2 pi, which is associated with a complete turn in radians, is 360 degrees, then we can say that pi radians is equivalent to 180 degrees, so we can then convert from degrees to radians and radians to degrees. So that's an important ratio to remember, that 180 degrees is pi radians, or 360 degrees is 2 pi radians. Because once we've got that, if 180 degrees is pi radians, what does 1 degree equal? If I know that 180 degrees gives me pi, what's 1 degree? It will be that pi divided by 180. So it's 180th of pi is 1 degree. And now that we know what 1 degree is, I could work out what 2 degrees is, 5 degrees, any angle. I just multiply the angle in degrees by pi over 180, and I'll have it in radians. Similarly, what would 1 radian be? If pi radians is 180 degrees, what's 1 radian, or 1 rad? It'd be 180 degrees divided by pi. That needs a bit of thought. If that's not obvious to you, you need to think about it, because otherwise you're always going to struggle to convert from one to the other. Really, all you need to do is remember this, that 2 pi radians is equivalent to 360 degrees. Once you've got that knowledge in your head, you automatically know then that pi must be 180, and then it's a case of understanding where this comes from. If 180 degrees is pi, then 1 degree you must divide pi by 180. And to go the other way, from radians to degrees, it's the other way, 180 divided by pi. So on your calculator, tell me what 40 degrees is in radians. What would I do? no, 1 degree is pi over 180, so 40 degrees will be 40 times pi over 180, which is radians. Degrees to radians, and in the assignment you're asked to do that, to complete a table and converting from radians to degrees and back again. So that's how you do it. Arc length, an area of a sector. So the arc length we've talked about, the arc length is r times theta. So if I just move this down and this down, so we've got already the arc length r theta, and we also have those two. So if arc length is r times theta, the area of a sector, if you think about it, the area of a circle is pi r squared. Thinking in degrees now. So then a part of a circle, a sector of a circle, and a sector of a circle is given like this. If I draw a circle and take a sector out, drawing from the middle, this is what I mean by a sector. Something that's taken out by drawing 2 radii from the centre and noting what bit we've taken out. So a sector of a circle is given by the area of the whole circle, pi r squared, and then multiplied by the fraction in degrees, so theta is over 360. In terms of radians, it turns out to be a half times the radius squared times the angle in theta, because the pi cancels out, and you could probably work out for yourself that that works. So we've got 2 formulas to find the area of a circle. If you were measuring the angle in radians, you'd use this formula. If you're measuring the angle in degrees, you'd use this formula. And that would give you the area of a sector of a circle. And again, you're asked to calculate that in the assignment. So this stuff on arc length and area of a sector is on page 156 to 7. Have a look at that. There'll be some examples of working them out in there. So how does this apply to this idea of angular velocity and linear velocity? A few definitions. This represents 2 rollers, one rotating anti-clockwise, so that's this one here, and one clockwise, going this way, and pushing out some material. So it's a process that you might see in a factory or something, where you're pushing through something, or some belt is being passed through between 2 rollers, okay? And this is moving with a linear velocity, so this is the linear velocity. And this is the angular velocity. So this thing's rotating. Omega is the angular velocity. So this symbol that looks a bit like a W is in fact omega. If you're drawing it, it sort of looks like a W, but it's more curly than that, sort of curled round on itself. The Greek letter omega, the lowercase omega, as opposed to the uppercase omega, which looks like that, the ohm symbol. So, for resistance. So we use the Greek letter omega to represent angular velocity, and there is a relationship, and I think you can see that in this drawing, between the angular velocity and the linear velocity. Because the faster I rotate these things, the faster this material is going to come out. And in the process, when you're, say, pushing out metal in a steelworks or something, or producing steel wire, you'll want to know this relationship between the angular velocity and the linear velocity. So I want to arrive at that here. Let's define a couple of things, a couple of terms. One is the number of turns of this drum. and that's n. So we're going to let little n represent the number of turns in the roller, and the frequency is that just the number of turns divided by time. So if this thing rotates, say, 20 times in 10 seconds, then 20 divided by 10 would give you 2 rotations per second. So the frequency is the number of rotations per second, and we get that by dividing the number of turns by the time that takes. So frequency equals n divided by t. So with that in mind and looking at this, I'm going to come up with an expression for the linear velocity of this thing, which is distance over time, down the left-hand side, so here. And then on the right-hand side, I'm going to talk about the angular velocity, which is the angle divided by time. But the angle is measured in radians, always measured in radians. We're going to come up with the formula, and I'm going to show you how they're arrived at. But at the end of the day, what you need to do is to be able to know what these formula are. What is the relationship between linear velocity and angular velocity? So long as you know the formula, it's not essential that you see how it's arrived at, but I think it's worth looking at it. Imagine this material coming out of this. So it's being produced between these two rollers, and it's coming out with a linear velocity v, and this linear velocity v is distance over time. What would be an expression for the distance that this belt's moved in terms of the rotation of this drum? The circumference, right. What's the formula for the circumference of this thing? Yep, or in terms of the radius, 2 pi r. But yes, you're right, pi d, but 2 pi r. Anything else for the distance? 2 pi r is the circumference. What else do you want to know? If we're after an expression for the distance this thing's travelled in terms of the rotation of the drums, 2 pi r, well, we're after the speed in the end, so imagine this thing rotating. Right, I want to know how many times it's turned, don't I? It'll be 2 pi r, which is 1 turn, the circumference, which is this distance right the way around, multiplied by the number of times it rotates. So 2 pi r times n is the distance this thing's travelled, divided by the time it takes. But we've got an expression for n over t. The number of turns divided by the time it takes is called the frequency. So in other words, v equals 2 pi r times the frequency. The circumference of the circle times the number of times it rotates per second will give us an expression for the linear velocity v. Now what about angular velocity? Angular velocity is defined as the rate at which it's rotating, literally, the angle divided by the time it takes. So imagine this thing rotating, and we've measured the angle it's gone through. So this angle here is theta. So we measured it at rotate. Well, actually, I've drawn it on the wrong one because it was going around clockwise, that one, but never mind. We've got the angle theta measured, and so I want to work out the complete angle this thing's gone through, which will be 2 pi, which is the complete turn, multiplied by the number of turns. It's the complete angle it's gone through. 1 turn is represented by 2 pi, as we've defined on the previous slide, and then n will be the number of turns. So the distance this thing's gone in terms of an angle is 2 pi times n divided by t will give us the angular velocity. But again, we have that omega n over t as frequency. So we've got omega equals 2 pi f. So now we have an expression for the linear velocity and an expression for the angular velocity. The question now then, how do I combine these two equations to come up with a relationship between v and omega? Omega equals 2 pi f. So instead of 2 pi f in this formula, we could write omega. So we can combine these two to get a very important formula that you'll use a lot that relates the linear velocity v and the angular velocity r. V equals omega r. And that's the formula that you need to remember and use. And this is how it's arrived at. In problems to do with angular motion then, we measure angles in radians. One complete turn is 2 pi radians. And we use the formulae v equals omega r and omega equals 2 pi f. These are two key formulae that you'll use, and you'll certainly use them in the assignment. Remembering that omega is the rate at which it turns, theta over t, measured in radians per second, so that's the angular velocity measured in radians per second, and the linear velocity, which is distance over time, measured in meters per second. So there is a relationship between the angular velocity and the linear velocity, and this is it here. So make a note of those formulae and the units. Okay, so have a look now at these questions here, questions on angular velocity. I'll leave them up there for a while and you can have a go at them using the formula that we've just written down there.